All right, equilibrium. What does equilibrium mean? Well, in its most basic sense, you've probably heard about equilibrium as it relates to biology. Equilibrium biology is the word homeostasis. So let's say you are at equilibrium temperature-wise with your surroundings. You are outside, it is January, and you are wearing a jacket. So we'll call this system U/jacket. Now, let's say you go inside, and when you go inside, you take off your jacket. So now we have U plus jacket. So the you and your jacket system, which we'll be talking about in a second, if you're comfortable and you're outside, you will keep on your jacket, which means you're losing heat and your body is producing heat, but your jacket is trapping it, so you're comfortable. Now, let's say you go outside in the morning, it's cold out, you have your jacket on, then you start doing some work outside, raking leaves or something, and you start to warm up. So what do? Well, now, because you have warmed up by generating more body heat by doing work, you have been stressed. Whereas before, you were at equilibrium, that is, wearing your jacket, you were comfortable, you will now shift to relieve that stress. So now, because you're producing more body heat, I'm going to erase this apart, you are going to shift by taking off your jacket. You're probably going to put your jacket on the ground, bring it inside, do something different. But the fact is, you and the jacket together as a system, whereas before you were comfortable in equilibrium, now that you are stressed because you have been doing more work and producing more heat, you have now shifted to deal with that stress. You've now taken off your jacket, if that makes sense. So that's the general concept of equilibrium. You have a chemical reaction, it's at equilibrium, and it's been stressed either by the concentration changing, the pressure changing, or the temperature changing, and how is that system or reaction going to respond to deal with that stress? Homeostasis is what it's normally called in biology. Okay, so let's go through these examples. We're going to use the example of the Haber, the Haber process, which is nitrogen plus 3 hydrogens reacts to form. We're going to use a double-headed arrow because, again, this is a system that can exist going in 2 directions. Reacts to form ammonia, 2NH3. Worth mentioning that this is probably, and the E, of course, stands for energy. This is probably the most important chemical reaction of them all. This is responsible for fertilizer, ammonia, which goes into ammonium nitrate. And I read that something like 40% of the nitrogen in your body comes from this reaction in the Haber process. Anyway, so let's talk about concentration. A couple of things to remember. My suggestion here, pause the video, write all this stuff down, write it down again, write it down again, write it down again, until it's just in your brain. Practice in writing. Once it's in your brain, then come back, make some, and it will be easier to make sense of this because these are the principles that we're going to go by. If you add something, it will use it. Okay, you want to think of this reaction as happening in a big tank, we'll say, and it's happening all at once. Constantly, you're having N2 and H2 combine, moving to NH3, but the NH3 is also going back and forming the N2 and the H2. If you add something, it will use it. Well, basically what you want to think about is you're going to open the door to this reaction, add something, let's just arbitrarily say hydrogen. Then after you add it, the reaction is going to be sealed back up, and now with excess hydrogen, how is the reaction going to respond? Again, when stressed, in this case by adding more hydrogen, how is the reaction going to shift in order to relieve that stress? So let's take a look at the example. If you add something, it will use it. So if I add more hydrogen, it will use it. Okay. So what does that mean? You can look at this reaction, you can see that hydrogen is reacting with nitrogen to form NH3 or ammonia. Well, if I add more hydrogen to the reaction, remember what happens after you close the door, the reaction is going to use up that hydrogen that I just added. Right over here, add H2. So if I add H2, it's going to use up the hydrogen that you just added. Well, what's it going to do with it? It's going to combine hydrogen with the nitrogen. After all, that's what the reaction is doing. So then the amount of nitrogen that you have is going to go down. When it combines hydrogen and nitrogen, what do you get? Well, you get ammonia. Ammonia goes up. So nitrogen's going to go down, hydrogen's going to go down after you add it, and then the amount of ammonia you get is going to go up. Again, if you add something, it will use it. Other ways to write this, you could say the reaction shifts towards the products. Because this is going up, it's going to shift this way. It's going to favor the forward reaction. As this reaction is written, it's written from from left to right, so the forward reaction would be this way. And we'll talk about this in a little bit. It's going to favor exothermic because, as you can see, energy is written as a product, and we'll get to this again later. And an exothermic reaction, you have your reactants and products, and energy is with the products in an exothermic reaction. Okay, so if you add something, it will use it. We added the hydrogen, close the door, it's going to use it, decreasing it. Nitrogen is going to also go down because it's combining with the nitrogen, and the ammonia is going to go up. Okay, let's look at another example. If you take something away, it will get it back. Okay, so let's say we're removing nitrogen. Okay, so we're going to take nitrogen out, and the reaction is going to try and get it back. If you take something away, it will try and get it back. Okay, so we take away the nitrogen. It tries to replace the nitrogen, so we're going to get more of it. Where does it get the nitrogen from? Well, it's not here, it's here. With that in mind, if you split apart ammonia, NH3, in order to get nitrogen, the amount of ammonia you have is going to go down. And along with the nitrogen, you can see, you're also going to get more hydrogen when you split apart the ammonia. So the amount of hydrogen you get is going to go up. So another way to say this is that it's going to shift towards the reactants. It's going to favor the reverse reaction. And it's going to favor an endothermic process, because if you look at this reaction from right to left, energy, with now the right side being the reactant side, energy is now being absorbed by the NH3 in order to make the nitrogen that you took away and the hydrogen. Let's do one more example looking at taking something away. Again, if you take something away, it will get it back. So let's say we're going to remove NH3. Okay, if you remove NH3, it's going to try and get it back. If you take something away, it's going to try and get it back. Okay, so we remove NH3. That means it's going to try and replace the NH3 you just removed. And what does it need to make NH3? It needs, of course, N and H. Well, where does it get the N and the H from? It gets it from this side. So the amount of N that you have is going to go down because you're using it to make NH3. And the amount of hydrogen you have is also going to go down because, again, it needs hydrogen in order to make NH3. Other ways you could say this is it's going to favor the forward reaction. It's going to favor also an exothermic process because energy is written on the right. And again, exothermic processes have energy written on the right. Okay, now we're going to move over to temperature. No, it looks like we're going to move down, but we're going to move over here to the right. So let's take a look at temperature. There are a couple different ways to think about temperature. I'm not going to talk about any of them other than the one that makes the most sense to me, which is to think of temperature as concentration in a sense. So with that in mind, we have to understand if you have reactants, products, and energy, when energy being with the product side, this is an exothermic process. If you have reactants plus energy and then forming products with energy with the reactant side, this means you have an endothermic process. So with that in mind, you can take a look at this Haber process that we have written up here, and you can see that it's an endothermic reaction. It's an exothermic reaction. The forward reaction is exothermic because energy is with the products, which means when you combine nitrogen and hydrogen, you get ammonia and energy. If you want to break ammonia apart, or look at this from the reverse reaction is endothermic because you need energy at the beginning, again, considering this from right to left, in order to break up the ammonia to make hydrogen and nitrogen. Now, if we're talking about the effect of of temperature, when stressed, a system at equilibrium will shift or relieve the stress. That is, we're either going to heat it up or cool it off or whatever. I like to think of temperature as it relates to concentration. So what that means is, let's say we are going to add heat. Okay, we're going to warm this thing up. Well, looking at the reaction like this, if I add heat, all I'm going to do is think of that as a reactant, or excuse me, as a participant in the reaction, and we're going to add heat by saying the concentration of heat goes up. Well, what does that mean? You can see if you add heat, what is it using heat to do? If you add something, it will use it. Well, if you add energy or heat energy, it will break apart the ammonia, which means the ammonia that you have goes down. When it breaks apart the ammonia, you're going to get more hydrogen, of course breaking it apart is NaNH, and more nitrogen. So again, if you add heat, the amount of this is going to go down, these two are going to go up because you can see that it adds heat in order to break apart the ammonia in order to get more hydrogen and nitrogen. Conversely, if you remove heat, and the heat energy you have goes down, well, if you remove something, it's going to want to try and get it back. Question is, how does it try and get it back? Well, if you remove heat, I realize I wrote this a little bit backwards kind of. Again, you remove heat, close the door, what happens? It's going to try and get the heat back. So the heat you're going to have is going to go up again. The ammonia you have is going to get up again because you get more ammonia when you get more heat, and the amount of nitrogen you have is going to go down, and the amount of hydrogen you have is also going to go down. So again, I think it's easiest to think of heat as something that's participating in the reaction like a chemical, and figure out what happens to heat from there, keeping in mind that exothermic reactions are written this way, endothermic reactions are written this way. Lastly, let's take a look at pressure. What you need to know about pressure. In general, more moles means more volume. Why is this relevant? Well, first let's talk about what this actually means. You can see on the reactant side, we have a coefficient of 1, even though we don't need to write it. You have a coefficient of 3, and then you have a coefficient of 2 on this side. So, with that in mind, you have 4 moles on the reactant side, and then you have 2 moles on the product side. What does this mean? Well, if you keep in mind Avogadro's law from earlier in the year, at STP, 1 mole of gas equals 22.4 liters, which is why if you are conducting this reaction at STP, 4 moles of gas will occupy a volume of 4 times 22.4 liters. 2 moles of gas will occupy 2 moles times 22.4 liters, which is to say more moles equals more volume. Now, one note about pressure that I didn't write here. If pressure increases, the reaction you'll have to just write this down. Pause the video and write this down. If pressure increases, the reaction will shift to occupy less volume, or which is to say it will shrink. If the pressure decreases, the reaction will shift to occupy more volume. Okay, so what does that mean for this? If I increase pressure, again, the reaction will want to shift. What does that mean? It's going to want to produce either more of this stuff or more of this stuff. So if I increase pressure, it's going to decrease its volume or shift to the side with less moles, because more moles is more volume. So with that in mind, if I increase the pressure, which side is that? Well, again, we have 4 moles over here, 2 moles over here, which means if I increase pressure, this is going to go up, and these two are going to go down. Because increasing pressure, the reaction can occupy less space by producing more ammonia and less of these two, because again, with 4 moles, this is more space than the 2 moles over here. Now, the converse, or the opposite of this is also true. If I decrease pressure, if you decrease pressure, the reaction is going to want to take up more space, which means it's going to shift to the side with more moles, which means you're going to get more nitrogen, more hydrogen, and less ammonia. Also keep in mind energy is involved here. So if I decrease pressure and it shifts this way, it's going to absorb the energy and promote an endothermic process as I move from right to left, because of course, moving to the left, as you can see these are going up, moving to the left, we are absorbing energy and promoting the reverse reaction, which of course is endothermic. Now, last thing I'm going to say, when you do these reactions and you keep taking a look at pressure, you want to note any subscripts that you see. So let's say you have A, which is a gas, you have B, which is a gas, and they are going to react to form AB, which is, again, a gas. All of these are gases. Let's just say we have, for the sake of argument, we have a 3 and a 2 here. Okay, so this is basically the Haber process as it's written up there, and then we have all these as gases. Now, gases are affected by pressure because gases are compressible. As you know from our mentioning of hydraulics and mechanical advantage, liquids are not compressible. That's why liquids in hydraulic pumps give us mechanical advantage. So, again, 4 moles, 2 moles. But keeping in mind these phases, if you notice that one of these phases is a liquid, now we don't count these 3 moles for this substance because it's a liquid and it's not compressible. So what that means is the number of moles that you have on the reactant side is not 4 anymore, it's 1. Because, again, this is a liquid and liquids are not compressible. So we only pay attention to the gases as it relates to pressure changes because gases are only compressible. So if you don't see a gas in this one location, you ignore the number of moles, which means your mole count for this is 1, your mole count for the product side is 2, and you would probably answer the question differently. So there's a lot going on here. Try your example problems, try your practice problems. Email me if you have any questions. Keep this stuff in mind. Be patient. This is a topic that takes a lot of effort and a lot of practice, but believe me, you can do it.